So this last lesson that we're doing in this unit is a natural extension of what we have been doing, okay? You've done linear inequalities. You did that in the last lesson. Earlier in this unit, you did systems of equations where you graphed two lines and found their point of intersection. And now we're going to combine those two ideas to say we're doing systems of linear inequalities where you graph two inequalities, shade the region that is the solution set, and what we're looking for now, since it's a system, is where they overlap. So a system of linear inequalities is made up of two or more linear inequalities. You're going to see an example with three later. And the solution of a system of linear inequalities is an ordered pair, any ordered pair that makes all of the inequalities true in the system. So areas of overlap, for example. The graph of a system of linear inequalities is a set of points that represent all the solutions. So you do it in the coordinate plane, and where they overlap is where you can count it. I just want to make a note here at the start, which I'll remind you of later. For something like this, being right here on the intersection of these two lines, this is a spot that works for the blue equation, because you can be on the line, you can be or equals. But for the red equation, no, because you can't be or equals. And when you're actually on the red line itself, that is where both sides of the red equation would be equal, or the inequality. So this doesn't work for the red equation, so it doesn't work for the system, okay? So you'll have to be in this area like that, okay? And of course, to infinity, because these extend beyond what we can see. So how would you go about graphing a system of inequalities? Well, you were going to graph these inequalities individually, and remember, you will shade the region appropriate to what this says y is greater than, less than, or etc. And note this. So the first thing you want to do when you graph these is you want to turn this, you want to think of it as an equation, such as y equals 2x minus 3. So you can find that boundary line. And that's what you're going to graph. And then you'll decide whether it's a dotted or dashed line before you draw it. And then once you do draw it, you'll decide which side you're going to shade it on. Something like this, though, that I'm going to mark in here in blue, it's not written in slope-intercept form. And although we've learned how to graph standard form equations like this, if you graph that, you won't know whether you're graphing above the line or below the line, because it doesn't say y is greater than or y is less than. So what can you do in that situation? Well, you're going to have to rewrite these into slope-intercept form. So how would you rewrite this into slope-intercept form? You would write, well, you would subtract 2x from both sides, and you would get y is greater than negative 2x plus 2. Okay? And of course, we actually want it to read like an equation for the moment so that we can find the boundary line. So that's what we're going to do. Now let's take a look at what they did in the example here. Okay. Graph each one separately. They're assuming you know how to do it from lesson 6-5, but I just gave you that little tutorial on it. You think of it as an equation in slope-intercept form. You say this got an intercept of -3, so down here, and then rise 2, run 1, rise 2, run 1, right? And then the actual original inequality says y is less than, not or equal to, so it's dotted or dashed, and then you shade below it. And if it's very steep, shading below it, you just imagine if anything dropped off of it, which region would it go, right? It would fall straight down into this area. This you have to rewrite, so we rewrite it like that. We have a y-intercept of 2 and a slope of -2, run 1, -2, run 1. Also, once we rewrote that, you want to then go back and say, okay, what does it look like rewritten so that we know what side to shade it on. And since it was pointed like that and there's no reason to flip it, it's y is greater, so you shade above it. And again, it doesn't say or equals, so it's a dashed line, and you shade above it. We're looking for the region in green. And by the way, this states here, have you seen these types of problems before? Sorry for the writing on that. But yes, of course you have. You solved linear inequalities in the last lesson, and you've done systems of equations where you graphed two lines and found their overlapping point, So we're now just looking for the entire overlapping region for inequalities. Okay. Note how they state the solution. They say the system solutions lie in the green region where the graphs overlap, meaning the implied idea here is that you need to do this visually. Okay, you're not going to write out it with some kind of equation or inequality where the solutions are. So you just need to show it graphically for systems of inequalities. And of course, you want to check some point that's in the green region in order to verify that that's correctly a solution to both equations at the same time. So they've picked the point 3, 0, because if you go over here, 3 units positive, and then don't go up or down, 3, 0 is right there. That's squarely in the green region. And when you plug 3 in for x and 0 in for y, we get 2 true inequalities. And so it checks out. Okay, get yourself some graph paper and see how you do with this. You really want to do this. Don't skip over this part because it's so critical that you get this. Now you might be going in reverse. You might be given a graph with a system of inequalities represented, and you need to write the system of inequalities that go with this. So first thing I'm going to do for you is I'm just going to zoom in on this so that you can get a good look at the values. Okay, just note this is crossing here at -1. This has a intercept of 5. Okay, this has a slope of 1, and this has a slope of -1/2. Okay, and the red one is shaded below and it's dotted. The blue one is shaded above and it's solid. Okay, all of that. So those are the things that we're going to keep in mind when we actually do this. Now, have you seen problems like this before? Yes, we did writing inequalities from a graph in the last lesson, and so now we're just doing it for 2 of them. It's just twice as many lines or inequalities to write, but nothing extra really to worry about. So how do you do it? Okay, we look for, well, this, let's say, yellow region is going to be for the red line, and this blue region is for the blue line. Okay, so the red boundary line is y equals -1/2 x plus 5. Remember we said y-intercept of 5, slope of -1/2, and it's shaded below and does not include the line. Okay, so y is less than that. The boundary line here is y equals x minus 1, slope of 1, intercept of -1. And since it is solid, it's going to be or equals, and we're shading above it, so y is greater than or equal to x minus 1. So you can start by writing that equation for the boundary line, and all you need to do then is swap out the equals for an inequality that's either greater than, less than, greater than or equal to, or less than or equal to. Okay, and so that's what the graph is showing this system. What are you going to do? Which equations would you do for this one? And I will take a little screen grab for you, zoom in on it. So first write the system of inequalities that are represented here, and it'll essentially just be 2 linear inequalities, one for the red line, one for the blue line. And then for this particular bit, the point here where the boundary lines intersect, is that a solution of the system? Explain. So the third and last example problem that we'll be doing today is modeling some real-world situation by writing and graphing the systems of linear inequalities. Okay, the real-world situation requires you to come up with the equations themselves after defining what the variables represent, and then graphing it to find the solution. Okay, it says that some real-world situations can have 3 or more restrictions, so you must write a system of at least 3 inequalities, and you'll get some practice at that in just a moment. So imagine this. You're planning what to do after school, and you can spend at most 6 hours daily playing basketball and doing homework. You want to spend less than 2 hours playing basketball, but you must spend also at least an hour and a half on homework, and you have to do this all in 6 hours or less each day, because it says at most 6 hours. What is the graph showing how you can spend your time? Well, what do we know? That the most we can play together, both variables when combined, will be 6 hours or less. We know that the basketball variable has to be less than 2 hours, and we know that the homework variable has to be at least an hour and a half. Okay. Now we need to find different ways or different amounts of time we can spend on each one, meeting these expectations. So what are we going to do? It says write and graph an inequality for each. We need to define the variables first, and then we're looking for that region where they are all coming together. But first we need to define the variables. So let x equal the number of hours playing basketball, and let y equal the number of hours doing homework. Notice that when they define the variables, they say, how are we measuring those things? We're using the units of hours, okay? Number of hours. So what do we do from there? Well, we write the system. We know that the number of hours playing basketball, x, and the number of hours doing homework, y, has to be less than or equal to 6, because at most, the most it could be is 6, and it can be 6, just that much or less. Okay? We know that x, the number of hours playing basketball, has to be less than 2, stated that less than 2 hours of basketball. The y variable, number of hours of homework, has to be greater than or equal to an hour and a half. At the least, the lowest amount is an hour and a half, so it can be an hour and a half, but that's the least it could be, so it's that or more. Okay? What do we do now? We graph this system. It can't be negative. Time cannot be negative, so it only makes sense in the first quadrant. We're not going to have a negative number of hours playing basketball or homework. Yep, so that'll be the boundary lines, those x and y axes. The solutions are all the points in the shaded region, so let's take a look at what we came up with. Okay, I can actually zoom in on this for you so you can just get a closer look. What we're dealing with here is the boundary lines. The number of hours of basketball going this way is got to be no more than 2, but it has to be greater than 0. There's no boundary line at the x-axis because we already know that it's got to be at least an hour and a half. So we're never going to have to worry about coming down and hitting that. Okay. Naturally, there would be a boundary there if we were able to, but in this case, we already know we're going to be having, for number of hours of homework, at least an hour and a half. So this whole region in here, not including this line because it can't be on that line, is possible combinations. So what could we say? We could say, if we picked a point, we could say, okay, then what about here? We could spend an hour playing basketball and 4 hours doing homework. Okay, that fits the got to be at least an hour and a half of homework, and it fits less than 2 hours of basketball, and also stays within the 6-hour limit. 1 hour of basketball, 4 hours of homework is 5 hours. Okay, etc. You can pick any point that is in the green region, and you can plug those numbers in, think about those numbers logically, and they will fit the situation. Okay, this will be challenging. Particularly, I want to point out for you, just as a little assistance, you're building a fence for a rectangular dog run. If you have a variable that represents the number of feet wide that the dog run is, a dog run is just an area where the dog can run around. And the dog run can be at most 50 feet long. You can have another variable for the length. Remember that if you're dealing with the perimeter, you are making fencing, so you have to go all the way around it. So you're going to have to travel in both directions along the width and the length. Keep that in mind when you're trying to write the equations for this, okay? But do your best, and we'll come back and see how you did. All right, so if we define x as the length in feet, and we define y as the width in feet, then x, we know the length has to be at most 50. It can be 50, but that's the most it can be. It's got to be that or less, okay? x is less than or equal to 50. And if y is the width, and we know that it's at least 10 feet wide, it can be 10, but it's got to be, that's the least it can be. So we've got y being greater than or equal to 10. Okay, we also know this. Notice this equation that they gave you, 2x plus 2y is less than or equal to 126. Can you figure out why this is the case, 2x plus 2y? Well, let's take a look. If we were to go along the length around, remember we're running a fence around this and we need to have it completely closed in to keep the dog in. So if we first go the width and then we go the length, we are not enclosing this yet. So we need to go the width again and then the length again. Remember, if it's a rectangle, we're going that distance twice to get around the perimeter. Just like you know, the perimeter of the perimeter formula for a rectangle is 2 times the width plus 2 times the length, sorry, equals the perimeter. Yeah? So once you know that, you can then see, okay, we got to have twice that width plus twice that height, length less than or equal to 126, okay? So how do we then graph it? Well, let's take a look at the graph. And what we've got here is this, these border lines that we have all or equal to, so they're all solid. And this natural boundary at 0, because of x is the length, and we know that the length is at most 50, so there's that line there, but it also is obviously 0 or greater. Yeah, so, well, and it has to be greater than 0. Obviously, the dog can't fit in there, so that would kind of be a dotted line there. Anyway, this is the area. If you picked some spot and you said, okay, what if I was using, let's say, 10 feet by 30 feet? That would be fine, because that would keep us under 126 if we went all the way around and would fit these parameters. All right, test your skills with these lesson check problems and restart. You'll see the answers after the break. Good luck with this. I know you can do it.